Hello, thank you for attending my talk about Mars, CERN, the Medipix detector and medical imaging. I'm Claire Chambers and I'm a doctoral student at the University of Canterbury working at Mars Bioimaging. In giving this talk I'm representing the work of the entire Mars team. That's a collaboration between CERN, who developed the chip itself, the privately owned company Mars Bioimaging, who are bringing this chip technology to the clinic in a new form of medical imaging, and also the New Zealand universities of Otago, Canterbury, Auckland and Lincoln, and various international research and medical institutions. This talk is in 3 parts. First, I'm going to talk to you about CERN and the work that they're doing. We're going to look at why they're doing research into high energy physics and how it fits into medical imaging. The second part is going to look at the physics in a bit more depth, specifically as it applies to medical imaging. Then thirdly, I'll show you some medical applications of this new technology. I'm going to keep the medical images to a minimum in the first 2 parts of this talk, so those of you who don't want to look at medical images may want to look away when we get to part 3. I'll let you know when we've got to that point. Here on the left is a picture of the CERN beamline. That's where they collide particles at very high energies in order to collect information about the earliest moments of the universe. What you're seeing here is the big concrete access tunnel that the equipment sits in. The equipment itself is big, powerful, supercooled magnets to control the speed and direction of the particles, and right in the middle you can see a small tube about the width of your thumb that the particles themselves actually travel in. Now, you might not think that looking up into the night sky is the same as looking back in time, or that studying huge stars and galaxies can tell us anything about the smallest particles that might once have existed. But in the 1920s, Edwin Hubble did some extensive work in identifying and studying galaxies outside of our own. Hubble discovered that nearly all these galaxies are moving away from us, and they're also moving away from each other too. Hubble realised that this means the universe itself is actually expanding. Now, light travels at a finite speed. It travels very, very fast, but it still takes time to travel. Because the distances in space are so mind-bogglingly huge, when we look up at distant stars and galaxies, we're seeing them not as they are right now, but as they were at the point the light started its journey from them to us. And because of those vast distances in space, that time difference can mean that we're looking back several billions years ago. In this way, we can look back to the first galaxies and even further, right back to 370,000 years after the Big Bang. And if we could go back around 14 billion years ago, we'd find that the universe somehow, through a process we don't yet understand, came into existence as a tiny, tiny dot and has been getting bigger ever since. Back when it was very, very small, all the same matter and energy that are currently in our universe were still there, only they were packed much closer together. And if you have a lot of energy in a small volume, that's another way of saying that that volume is really hot. Now, a big change happened 370,000 years after the Big Bang. By this time, the universe had expanded and cooled enough that atoms could form. Once atoms could exist, all the structures we see around us today, like galaxies and stars and planets, could finally start to form. This was a massive change to how the matter in the universe was structured, and it allowed light to travel long distances in space. Before then, the universe had been too hot for atoms to form, and instead all the parts that go into making atoms, or the electrons and neutrons and protons, existed in a kind of electrically charged hot soup known as a plasma that even light couldn't get through. So the furthest we can look back using light is to 370,000 years after the Big Bang. What we do know is that if you go back even closer in time towards the Big Bang, the universe gets hotter and hotter, and the particles that existed become increasingly fundamental and strange. The way scientists gather this information is by using particle accelerators to recreate the high energy conditions of the early universe. Because of these experiments, We now know that protons and neutrons are made up of quarks, and there's a whole family of particles related to the electron. But there's still a lot about the universe just after the Big Bang that we don't know. We really want to know what things were like back then, because it will help us explain a lot of things about the universe that we don't understand. Like, why isn't there the same amount of antimatter as there is matter? What is mass? And electrical charge? And gravity? And time? And where did the universe come from anyway? I said that the way that CERN and other particle accelerators look for answers is to dump huge amounts of energy into a very small space and try to recreate those really hot conditions right after the Big Bang. They do this by accelerating big heavy atoms, the heavier the better, as fast as possible around a big circle. Then they smash these particles into each other and look at the bits that fly out. Here's a diagram of what one of those collisions might look like. What you can see is that these collisions get really complicated, with lots of particles flying off in different directions and sometimes only existing for very short periods of time. And the fragments can be made of very different types of pieces. Some pieces might carry charge and others might be just energy, and another piece might be the bit of the particle that gravity works on, the bit that gives the whole particle its mass. We call that part the Higgs boson, by the way, and this is how CERN found it. We'll talk about that in a few slides' time. CERN accelerate particles very fast around a 27-kilometre long ring that sits underneath the France-Swiss border, right next to Geneva. You need a very big ring to accelerate the particles up to the highest possible speed, and you also need a really big, really sophisticated detector to track all the fragments as they fly apart. Now, because CERN are doing science that nobody's done before, they have to build their own equipment that's capable of doing it. So they have a long history of designing and building their own detectors. And back in the 1990s, they started using what they called then the photon counting chip, which could not only register the interactions the particle fragments have with a detector, these new detectors could also measure how much energy each fragment had. Now, along the ring, there are these big arrays of equipment, these solenoids. The particle collisions happen inside these solenoids, and what you see here is the equipment necessary to detect and measure and record these collisions. You can actually see the scale of these solenoids by the people standing in the bottom of the middle picture. When this solenoid is installed in the beamline goes through that central hole, and that's where the detectors sit that we're going to look at next. The photon counting chip was later renamed the Medipix chip after CERN started thinking that it could be incredibly useful for medical imaging. It's gone through a couple of upgrades since the 1990s, but the basic principles are still the same. The detector on top is a semiconductor. Now, a semiconductor is a material that isn't a conductor and it isn't an insulator. It behaves somewhere in between, meaning that electrical signals can pass through it under very particular conditions, and what those conditions are determined by the materials that the semiconductor is made of. Semiconductors are really sensitive at detecting radiation because the incoming particle creates a splash of charge, basically a sudden pulse of electricity. It's this sudden splash of current that we want the semiconductor to be able to conduct. Now, under the semiconductor, there are some really clever electronics. The semiconductor sends the splash of charge back to these electronics, and they measure the energy of the radiation particle according to how big the splash was. The size of one of the detectors as a whole is around 14 millimeters square, and it's split into 256 by 256 pixels, which are capable of seeing features as small as the thickness of a human hair. I want to talk a bit more about that incoming splash when the radiation hits the detector. I said that the electronics count the number of pulses and they measure how powerful the pulses are, because the amount of splash created is a good guide to the energy of that incoming radiation. But sometimes the radiation can splash out across several pixels, either because it has a lot of energy or because it hits at the edge of a pixel. One of the really cool advantages of the latest version of the Medipix chip is that the electronics perform charge summing. That is, when neighbouring pixels record a signal at exactly the same time, these signals are combined and treated as a single event that occurs within the pixel with the highest count. So in this example, a single incoming ray with 100 energy units looks to the detector like several rays with much lower energies. The electronics sums up these events that happen at the same instance in neighbouring pixels and adds them up to be a single event with 100 energy units occurring in one pixel. Doing this significantly improves the accuracy of the energy measurement that we can do. Now, CERN deal with a lot of different types of particles, so I'm going to look a little bit about what those particles might be. An atom has a central nucleus which is made up of protons and neutrons. The protons have a positive charge, and it's the number of protons which determine which element the atom belongs to. All atoms of carbon have 6 protons, all atoms of nitrogen have 7, and so on. The neutrons have no charge, and their number inside the nucleus can vary. Each atom also has an electron cloud surrounding the nucleus, and these each have a negative charge. The number of electrons is the same as the number of protons, so that each atom in its simplest state has a neutral charge. Radiation can take many forms, so I'll give you a few examples. It can be neutron radiation, those neutrons being ejected out from the nucleus at high speed. It can be protons, or it can be electrons, which we sometimes call beta radiation. Alpha radiation is a heavy composite particle made up of 2 neutrons and 2 protons in combination. You can also have particles of pure energy. These are confusingly called photons, not protons but photons, and can also be called gamma rays or Xrays. What they are is a high energy form of light, and we're going to mostly refer to them as X-rays from now on. Under the high energy conditions inside a particle accelerator, protons and neutrons can be split apart into quarks and antiquarks, particles we never normally see because they can't exist individually in today's universe. Quarks in the matter around us have to be packaged inside other particles in pairs or threes. They haven't been able to exist separately for over 13 billion years. Under high energy conditions we can free these quarks, and we can also watch them combine into exotic combinations that aren't able to exist nowadays. This July, CERN discovered the tetraquark, a particle made up of 4 quarks together that hasn't existed since shortly after the Big Bang. Unlike protons and neutrons, though, it seems that electrons don't break down into smaller particles. Instead, they are the everyday members of a strange family that includes muons, neutrinos, their antimatter cousins, and more. You can also see in this table a group of interaction particles. These are tiny packages of energy, each one carrying a different type of energy relating to a different kind of force. There's a different type for each of the different forces. The one that's familiar to us is the photon. That's a package of the electromagnetic force. There are others. The atomic nucleus is held together by 2 forces that we never see in normal life because they have very, very short ranges. These are called the strong and the weak forces, and they have their own force particles, the gluon, and their Z and W bosons. We take mass for granted, but what CERN have found is that in the very early universe, particles didn't have any mass at all. What they've found is that mass is a property of matter that comes from matter interacting with an energy field, the Higgs field. And the particle that carries this energy is the Higgs boson. In the very early universe, the Higgs field had a value of 0. As the universe cooled, the Higgs field grew, and any particle that could interact with this field acquired mass. This is pretty mind-bending stuff. But CERN's discovery of the Higgs boson in 2012-13 was proof that the universe really is this strange. Here are a few of the people involved in discovering the Higgs boson at CERN. Discovering the Higgs boson was a really big deal because it supported what's called the standard model of physics, which is all the detail I've told you about the different particles and the different force carriers. It was a big triumph and a big relief to find the Higgs, because some scientists had started to wonder if it might not exist at all. This would have been pretty embarrassing because it would have meant that the standard model was wrong, and physicists would have had to go back and come up with a new explanation. So I've talked about how CERN are interested in detecting and measuring all sorts of different particles. But for medical imaging, the most common form of imaging is done with X-rays. So from now on, we're going to look at the applications of Medipix for recording X-rays only. Okay, here we go. X-rays were discovered in 1895 by Wilhelm Röntgen. Here is one of the earliest X-ray images ever taken. And for the next 80 years, the basics stayed pretty much the same. You have an X-ray source, an object being imaged, in medicine we call this the patient, a detector of some sort, and a pattern recognition system, which is probably called a radiologist. And for the next 80 years, the equipment and the quality of these images improved massively, but the basic principles stayed the same. And so did the output, a two-dimensional flattened image. Then in the 1970s, Hounsfield and Cormack made a really significant breakthrough by inventing computed tomography. The idea is that instead of taking one image, you take lots of images from lots of angles around the patient. From these, you can work backwards, mathematically, to reconstruct the image into a 3D image. So, whereas previously an X-ray of a skull would produce the sort of image you see down here at the bottom of this grid, with the structures of the skull messily superimposed on one another, in a 3D render you can now see where exactly those features are in 3D relative to each other. This is really useful when dealing, for example, with complex fractures where you really have to see how the fracture and the damage relates to the whole volume. And it turns out that the same technique for assembling these three-dimensional images also massively improves the ability of X-rays to image soft tissue. The discovery of computed tomography was regarded at the time as second-generation X-rays. And we at Mars, we believe that multi-energy, spectral energy, CT, is the third generation of X-ray. And that's why we're working so hard to bring this into hospitals as soon as possible. So here's the staff of Mars Bioimaging at the University of Canterbury here in New Zealand, together with some of our partners who are working towards this with us. X-rays have colour, because X-rays have a range of different wavelengths, just like visible light does. For visible light, we can see these different wavelengths as different colours. So red has a longer wavelength than green, and green has a longer wavelength than blue. I'm going to call this type of X-ray colour true colour, because it relates to the wavelength of the X-rays in exactly the same way that visible light has colours that relate to the wavelength of its photons. Later on, I'm going to talk to you about false colour, which is arbitrarily assigned to images by a computer, so that when we look at those images we can easily pick out the differences between the different behaviour of material in those pixels. Now, when X-rays interact with matter, they do so in different ways, but at the energies that we use for medical imaging, they interact with the electrons around the atom. Every different element has a different number of electrons, and these electrons arrange themselves in different ways in different energy states around each element. This means that each element has a distinctive response to X-rays, but there's also an energy dependence in that response which complicates things. If we imaged a person, this is meant to be a person seen from the head down, what we get is an image made up of all the different materials in their body, responding to all the different energies in the beam. And you'll know that when you have a dental X-ray, for example, some features like your teeth show up really, really clearly in the image, but other things, soft tissue things like your gums, your cheeks, your tongue, hardly show up at all. And this is because some materials have a much bigger response to radiation than others. So the X-rays in the beam and the calcium in your teeth together have a much stronger interaction than the X-rays do with the soft tissue in your tongue. As far as energy dependence goes, the general rule is that high energy X-rays go through matter with far fewer interactions than low energy X-rays. So for dental imaging, your dentist may go behind a screen or outside the room to protect themselves when you're being X-rayed. Much higher energies of X-rays could go through several meters of lead, and really, really high gamma rays can pass through the centre of the Earth without interacting with anything at all. And generally when we look at how material responds to radiation of different energies, we get these decaying exponential curves. So lots of interactions at low energies, much fewer interactions at high energies. Now you'll see from this graph that some materials have these sudden increases in their responses at particular energies. These are related directly to features in their electron shells, and they're really useful for identifying exactly what the material is inside the object. Unfortunately for us, most of the materials that occur in people don't have these sudden increases at an energy that we can usefully use. So instead we have to look at the behaviour of the material across the whole energy range. Normal CT images sums up the interactions within a small volume across all the beam energies. The output of this sum is one single value for each material. That's enough to tell bone from soft tissue, but it can't tell us any more than that. With the Medipix detector, we can investigate that energy behaviour much more closely and look at the material's response at multiple points across the energy range. This gives us a lot more information that we can use to work out what the material must be. So, to recap, each different type of material has its own distinctive response to radiation. If we can measure this response, we can identify what material we have in the object. And not just identify it, but we can also quantify it. We can measure how much of that element is in each tiny little volume within the object. Now this is where we come back to talking about our other type of colour, false colour. And I need to explain to you what you're seeing here. This is an X-ray image of what we call a phantom. A phantom is a standardised object that we use for calibration purposes. And in this case, it's 12 vials containing different solutions held together in a holder. I said that in the previous slide that each material has its own distinctive response to radiation, and we can measure that response and work backwards to figure out what the material that's causing that response is. Let's say that we allocate a false colour to pixels in our image on the basis of those different responses. So say we allocate white colour to pixels that have one particular type of response, and green to those that have a different type of response, and red and yellow and blue and so on. What we find is that just by doing that, we've identified the vials that contain the same materials. So in this case, here you see that we've coloured both the calcium vials white, and we've coloured the gadolinium vials green, not on the basis of knowing that those materials were in those vials, but simply by looking at how those materials in those vials have responded to radiation. And as you can also see, we get some clues about how much of those materials is in each vial. Okay, but so what? How is this useful? Well, say that researchers have developed a drug to kill cancer. Wouldn't it be good to know whether that drug actually reaches the cancer, Or does it go to the patient's kidneys instead, or to their liver, or to their big toe? With this technology, you can attach a nanoparticle to each molecule of the drug, and then you can use material imaging like this to see exactly where the medicine goes inside the patient's body. This sounds pretty space age, but it's already an accepted technique. Gold nanoparticles are a common choice for this, and as you can see here, our detector can identify the response of gold to a beam of X-rays. So doctors could give a patient this drug and then image them in real time to find out how the drug is reaching the tumour. Now we've reached the point where we're going to look in some more detail at some medical applications. So this is the point where people who don't want to see medical images should stop watching or look away. Still here? Onward. This is my boss having his foot imaged. He's the first living person to be imaged in full colour. Now, CT imaging is generally considered quite a high dose procedure, but the Medipix detector works in a different way to normal medical detectors because it counts and measures every single X-ray photon individually. This means that we can get images with far more information in them compared to conventional X-ray images, but without increasing the dose to the patient. Here's a computer reconstruction of the data from this scan. I want to be perfectly clear that this image has not been artificially coloured by hand. These colours that you're seeing are assigned solely based on how the material in each tiny little volume responded to radiation during the scan. The proof of the technique is that after we've done this, we can clearly see all the structures we expect to see in a foot, both the bony ones that we can see with normal X-rays and the soft tissue ones that we'd otherwise need for the patient to have an MRI scan to show us. So here we see the bones, which we've allocated a false colour of white to, and the soft tissue, which is red, and the fat pad of the foot, which is pink. So if you injured your foot today, how would it be imaged? At the moment, there are two main options. Conventional X-ray is brilliant at seeing bone, but it's pretty rubbish at seeing soft tissue, particularly when compared with MRI, magnetic resonance imaging. MRI is great for seeing soft tissue, but it's pretty rubbish at seeing bone. MRI is also not suitable for some patients if they've got metal fragments inside them. They're expensive and they have pretty rubbish spatial resolution. Wouldn't it be nice if you could see the soft tissue detail that MRI gives you, along with the bone detail that X-ray gives you? Well, with Mars imaging we actually can do that, and we can split it up into different channels as well, so that you can see the calcium and the bone structure in the bone channel, but you can also see the water channel, so all the tissues which are rich in water, and similarly all of the tissues that are rich in fat. We've had some epic publicity from the images that were taken of my boss's foot and wrist. Now we're moving on to trials on patients. I'm going to show you a couple of applications of Mars. Firstly, I'm going to show you a soft tissue imaging application. Now, Atheroma is a kind of gunky scab that forms inside blood vessels. It's a mixture of calcium and fat deposits and maybe a blood clot or two. If these break away from the blood vessel wall, the shards get swept along in the bloodstream, and eventually they can reach the heart, the lungs or the brain, all of which are really, really bad news for the patient. These Atheroma become pretty common in middle age, but actually they're not usually a big risk. The ones that are really dangerous are the ones that contain a lot of liquid fat, but previously it hasn't been possible to identify which ones these are until they suddenly rupture. So this is part of a carotid artery. That's one of the big arteries that goes up each side of your neck and supplies each side of the face and brain with blood. This one was removed surgically from the patient before it ruptured because it was believed to contain a very high risk atheroma. When we scanned it and did our material analysis on it, we were able to see exactly how nasty this atheroma actually was. We were able to see that fatty necrotic liquid core inside the wall of the blood vessel artery. This is an example of what we can do imaging soft tissue, which we're currently now trialling in living patients. Now I'm going to show you an example of bone imaging with MARS compared to conventional CT and dual energy CT. Dual energy CT is a kind of halfway house between conventional CT imaging and the spectral imaging that MARS does. Dual energy uses two energies, so it can provide some material information, but usually very, very limited information. So what you're looking at on screen now is the image of a joint, and you'll first of all be able to see that the spatial resolution of the MARS image is much better than either of the other two. Bone has this honeycomb internal structure that we can see much better on the MARS scan, and the honeycomb nature of this internal bone tells us a huge amount about the strength and health of the bone. It can tell us whether a fracture is healing properly or if it isn't. Another of the really useful features of MARS technology is that we're able to reduce the artifacts that metal objects cause in X-ray images. Now, this joint had a screw added. If you fracture a bone in a complex fracture, a surgeon may need to put in screws or pins like this to hold the pieces of the bone together in the right places until it has time to heal. But there's a big problem with these implants on conventional CT, and that is that the metal in the screws casts a kind of X-ray shadow around the edges of them. If you look closely around the screw in this dual energy CT image, you'll see a dark region where the bone and the screw meet, where there's no image data at all. Now, a gap between the bone and the screw is a sign that the bone is rejecting the screw. But the shadow is a problem because we can't actually tell if there's a gap or not. On the left of the screw in the MARS image, you can see quite clearly that the bone goes all the way up to the thread of the screw. So we can see that the interface here is nice and tight. We have great assurance that this is a really nice bond between the two materials. On the other side of the screw we can see a dark region, so we can be pretty sure that the gap in that region is a real gap. We're currently trialling this now on fracture healing, particularly on fracture healing where there is complex breaks and multiple metal implants. Now on the right here we have another image of the boss, in this case his wrist and his watch. Here we're seeing the power of the Medipix imaging scans as essentially a kind of X-ray microscope, and it's a microscope with much broader applications than medicine, even though that's our primary focus. So I just want to touch on some of the non-medical applications of this technology. My personal interest is in using the technology to non-destructively investigate fossils. We've also been exploring applications for imaging in geology and mining, the quality of meat for the food industry, and providing better border security, so better material analysis of what people are bringing into New Zealand, and also better spatial resolution to identify insects and other pests that would damage our ecosystem. Going forwards, what we're currently gearing up for now is our coming product launch of an arm and wrist scanner. What we've found is that foosh injuries, that's fall on outstretched hand, are incredibly common, have a massive effect on patients' quality of life, and are extremely expensive for ACC, which is the body that funds medical care for accidental injuries in New Zealand. We know that around 15% of foosh injuries are misdiagnosed, and what we want to know is whether, using the enhanced scanning and imaging capabilities of the MARS scanners, can we provide a more accurate and faster answer to the question, why does it hurt? That wraps up my talk. Here's a little bit more information about us and about some of our partners, both in New Zealand and overseas. You can find out some more information about us and contact us through our website. Thank you for listening to my talk and enjoy the rest of your Worldcon. Thank you.